Okay, so now what we need to do is kind of take a look at chemical and physical changes and be able to describe and also sketch what's going to be happening in terms of changes at the atomic level. So this right here would be, this is a simulator, and so this is showing solid oxygen. Solid oxygen does actually exist. It's kind of neat. It's blue when it's solid, and it's actually magnetic. You can move oxygen back and forth with a magnet. Which most people don't know because most people don't see solid oxygen. But anyway, we were taking a look at water. So let's switch this over to water. And this would be water in the solid state. We didn't see water in the solid state. We saw water in the liquid state. So let's heat this up a little bit. Okay, that structure that it had where they were sitting there and vibrating, and the particles were sitting in a fixed position, but they were just moving. There's always some kind of motion of the particles. When they're in the solid state, they stay in the same spot and they just vibrate back and forth. In this state right here, when something's a liquid, the particles are still touching each other, but the difference is they don't have that what we call lattice structure, and they're not in a fixed position, and they can start moving past each other. Let's heat it up a little bit more. Okay, we're still in the liquid state. One of the things that a lot of people don't realize, that temperature is actually a measure of the kinetic energy of the particles. So the more temperature you have, the faster the particles are moving. Or, other way around, if particles are moving faster, they have a higher temperature. So we actually do something where we measure the speed of the particles by moving the temperature. That's going to be an important point as we move forward in the year. All right, so if you take a look at this, let's kind of keep heating this up. That was what was happening with the water that I had on the heating pad. And you should notice they're getting a little more energetic. They're getting a little more energetic. And now you see they start gaining a lot of space in between the particles. So this is when a lot of this is gas. Now some of this down in here where they're close together, those are still actually in the liquid state. I can heat this up a little bit more to see if I can get a few more of them become vapor. And so we'll take a look. What would you have to be able to do with this on paper? Obviously, you can't do an animation on the piece of paper. What kind of stuff are we going to expect you to know? Well, if they ask you to draw something in the solid state, you have to have the particles touching each other, and you could describe that they're vibrating, but they're not sliding past each other. They're not moving past each other. In the liquid state, they could be the same distance or a little bit further, a little bit closer together, but the big thing is now they can move past each other. So we'll say that they're rolling around. What's the difference in that? In terms of the physical properties, when something's in the liquid state, that means then we can pour it. In the solid state, whatever size it is, that's the size it stays. So its volume, it won't take up the volume of the container. It'll just sit there in a nice chunk as to whatever it is. Now what we have is when they're in the vapor state, the particles have so much energy, are moving so fast, they fly apart, and they might interact a little bit. If you notice these things, there is some interaction going there. We're going to cover that a lot later. But there's quite a bit of space between the particles. In this particular situation right here, unlike when they're a solid or a liquid, instead of having a fixed volume, they expand out and kind of take up the volume of the container. Okay, so that's the stuff that's going there. The bubbles that you were seeing that were coming from the bottom of the beaker were still water. What we did is we just heated up the water particles, and what you were seeing come to the surface was actually little bubbles of water vapor. So they're little steam bubbles is what they were. That's what we call a physical change, because structurally it was the same substance both before and after the interaction. Okay, so that's that. Let's go to another sim. Okay, in this particular sim, okay, so it's going to wash me out a little bit because it's a lot brighter screen right here, but I think we can still see it. You had some water molecules. Now, some of the things when you're drawing a water molecule, they're going to expect that you have actually H2O. Okay, the oxygen's the bigger molecule, and they want kind of a little bend on it. So the waters are actually on one side. When we get into drawing the shapes of these and stuff, you'll see, why we have them on one side. When I put electricity through here under the right circumstances, we get something different. That was electrolysis. Those bubbles we were seeing were not water molecules. They were not steam. What we actually had happen is you had the water molecules actually breaking apart, so you're breaking the bonds. So the electricity will actually break the bonds between the hydrogens and oxygens right there. And then the hydrogens would bond with each other. So the one that was streaming up really fast was actually bubbles of hydrogen gas. And in the other one, you get a big bubble once in a while, and that was going up into the top of the test tube. That was actually bubbles of oxygen gas. What we'd expect you to do when you're showing something like this is when we say to sketch it, you'd have to show water molecules, and you have to have the same number of atoms on each side, but the atoms would have to be rearranged into the new chemical components that you get in the chemical change. So that's the difference between a chemical change and an actual physical change. In the physical change, got the same mass before and after, so conservation of mass, and all these changes, if we capture everything, we don't have a change in mass. But in a physical change, it's the same exact substance before and after. In a chemical change, we break some bonds, we form new bonds, and we end up with new chemical substances than we had before. Okay? Now, another thing that goes along with this is we learned in the 1700s and at the beginning of the 1800s, we started seeing this conservation of mass so much that we called it a law. What does that mean? In changes in chemistry, as long as you can capture every single thing before a reaction occurs and after the changes occurs, there will be no change in mass. But they didn't have any kind of theory or explanation for it. So around 1810 to 1820, right in there, scientists came up with what we call the law, or an atomic theory. So how does that theory work? Well, they said all of these different elemental substances are actually different atoms. So the red ones here would be oxygen, the white ones would be hydrogen, but elements, these different atoms of stuff, couldn't be created or destroyed. So as long as you're capturing everything, what's really critical, if you're trying to show this, is the atoms would rearrange, but you have the exact same atoms there. When these atoms rearrange and form new bonds, you get new substances. So this was our first theory that was actually an explanation of the conservation of mass law. So I hope that kind of makes sense. This is something you'll be asked to do on the AP test. So what they found is a lot of students can go through and solve a whole bunch of problems, but they really don't have any idea what's going on. So this is going to be a huge thing. What we're doing when we're balancing chemical equations is we're actually making sure in the chemical reaction that the total atoms we start with are the total atoms we end up with. And that's always part of the grading system when you're asked to do some kind of a sketch of a chemical change. So you got to have that in there. Same number of atoms, both before and after. Now this is a theory. Theories are models that we use to explain things. The conservation of mass law is something that just is. We know in all these changes, mass is always the same before as after, as long as we gather everything. Atomic theory is a model that we use to explain the conservation of mass law. So during almost all of the 1800s, we were treating all these chemical reactions theoretically as if they're these little spheres or balls of different mass where all the oxygens were the same, all the hydrogens are the same, all the irons are the same, but an iron is different than an oxygen, and an oxygen is different as a hydrogen. And so all chemical reactions were just, rearranging these little spheres. That's it for this.